Good afternoon, everybody, or good morning, or good night, wherever you are in the world. Today I want to talk to you about our active suspension. And before we get started, I'm actually going to just introduce our active suspension to you, that you have an idea what we're talking about. And as you see in the picture here, we have a base unit of the active suspension, and this gray plate here is going to be our road model, and this road model we can actually change the height of it. The red plate here represents our tire, and then the blue thing that's wiggling on the top, that's going to be our car model. And as you can see, if we hitting a bump, then the car model is going to jump up and down, and that's usually behavior that we don't want to have. So a little bit more about the hardware. Right here we have an encoder installed that we can actually measure how much our car model is deflected from the base of the unit. Back in the end here there's a black box that is our accelerometer that we're going to use to actually design an observer later on in this presentation. And right in the center here there's actually a motor that we use to dampen the effect of the active suspension when it hits an obstacle. Over on the right side here, this is actually our amplifier that we use to drive the model, and on top of the amplifier is our data acquisition board, and as you can see there's a lot of cables going in and out, and this is just because this is one of our more advanced models that we're using in hardware, our more advanced models that we use for controlled education. As this is one of our more powerful units, this unit comes with a hardware watchdog. That means that no matter what you do, the unit is protected from harming itself. So there's a fairly large DC motor in the bottom that's going to drive this road model. So we go up and down, and there's physical limits to how much up and down we can go. And to protect our hardware, there's a watchdog that basically kills in the end. Now, what I'm going to talk to you about today is basically going from your standard design of a controller for a known plant and design a full state LQR controller, and then we extend this to actually showing how we can actually use a proper full order observer design to get to an LQG design. Usually what you come across in your state space classes is the problem that you have your wonderful A, B, C, and D matrices of your state space model already given, and you are asked to find an LQR controller. And the LQR controller comes in, or I have actually built this model here. As you can see, here's my A matrix, my B matrix, my C matrix, and my non-zero D matrix here. And then in this model here, you actually can see that I have already the observer built in, but for now we're going to leave the observer out and just look at the full state space representation. So I actually plug into the state space representation right here and actually extract all the system states. Now note that this is something that I can do easily in Simulink or LabVIEW, but in real life this is not as easy. So this is actually just to show you how nicely I can do this in the simulation. Now what we do in MATLAB is basically we can just say, let's say our gain is called K3, we can just then say if our system matrices are known to the system, we can use LQR, say our A matrix, our B matrix, some weighing matrix Q that I've already have in the workspace, and some weighing matrix R to actually have all the parameters for our Riccati equations. Press enter and we get an error because my R matrix is not the right size. Hold on. This is because my B matrix is actually larger than it's supposed to be. There we go. There we go. After a little bit of back and forth, I actually managed to convince MATLAB to do what I wanted to do. And what you can see here, we actually get a K3 that is a row vector with 4 entries. These 4 entries are the entries that we need that correspond to all our system states. We already, as I said, we already have our system matrices A, B, and C available. And just to give you, just to make sure that we all see what's going on, here's our system matrix A. Now these values here, these are values that we actually determined before with the physical model. I'm not going through this today, but just to give you an idea how this actually looks, we basically have in our background section of our active suspension, we actually go through the whole modeling process. So we actually have a block diagram model with all the spring constants and our damping coefficients and our coordinate system, and then go through the derivation process of how to actually find our system equations. And after a lot of math and explaining, we end up with a system equation that looks like this. And this is the equations that we're actually going to use here. So as you can see, we have a C matrix that will give us 2 outputs of the system, and a B matrix that actually requires 2 inputs. Now this B matrix in particular requires 2 inputs because we're not only trying to control our car model up here, but we also have to design a controller to actually move our road surface platform to our desired location. And this is why we have 2 inputs. One input is driving the lower motor for the road surface, the other input is driving the upper motor for the car control. So with these models already in MATLAB and now with the controller that we have obtained, we can then just go to our Simulink model and say, I'm just going to change the value of k here and say, call this k3, and can just close the loop. So in here, no, this is actually the hardware model. I want to go in the simulation for now. So do the same here. In here we have our model up here, and we're taking our system states and then vector multiplying them with our LQR gain, sending them through a saturation block because we eventually want to implement this with our hardware, so we have to make sure that we don't have gains that approach some large value that we can't deal with, and then directly feeding them back to our system. So if you are familiar with Simulink, you notice that we're actually running an external mode, and this is basically to make sure that we get a real-time response. Even though this is a pure simulation, this is running on our external kernel where we make sure that our time constraints are met. So if I now run the model, I can then look at our output, and this is basically what we see if we don't have any control. The yellow line that you can see here is basically our road surface moving up and down, and then the pink and blue lines is what happens to our platforms, and to the red platform and the blue platform respectively. And we can see, well, there's quite a few oscillations going on, and even though they are decaying in magnitude, we don't really settle to where we want to be. So this is not a desirable outcome. However, this is with 0 input. Now if I actually choose to connect our LQR control design that we just did, and just flip the switch here, then I have a very different result. Now I actually can see that my model of my car tire and my car itself quite quickly settle to where we want them to be. And this is quite a nice behavior. Now of course, since this is MATLAB, we can then just go back to the workspace and say, okay, this is quite a nice behavior, but let's say I want a different weighing matrix Q. So I can just go in here and say, I want to build a diagonal matrix with the diagonal entries 1, 2, 3, and 4, just for the sake of an example, and we run this thing again. Now you can see we have completely different gains now, and this is just because our weighing matrix have changed. And this is exactly what we would expect if we change the weighing matrix, that we get completely different results. So let's see if that actually, how this actually works in our simulation model. Once again, I connect to the target, our external kernel, and run it. And now, if you look at the result, this is still quite oscillatory, even though it is running with the controller. And this is just because our weighing matrix has changed. So clearly the choice of weighing matrix has a huge impact on how well our system actually performs. So we would actually like to have a performance that is closer to the first one. And this is something that's very nice to show in software and simulation, but for students it's usually not that easy to wrap their head around what does it actually make, or does it actually make sense for real life. And so we actually have a hardware model of our system as well. Now for the hardware model, one of the first things is we have to actually talk to the hardware. So if I click in the subsystem of our actually active suspension, we have a couple of blocks that I would like to point out. One of them is our hill initialize, and this is comes with the Quark toolbox that you get access to once you purchase one of our products. That basically connects our hardware to the Simulink environment. And then we have sensors that we want to read, and in this case these are encoders and analog signals that we want to read, and we basically just introduce blocks from our Quark toolbox once again and can read the signals directly. Once we read a signal, we actually have to make sure, for encoders for example, we read how many counts actually represent what kind of displacement we're talking about. So we actually have to have a sensor gain to actually make sure that whatever our sensor information we get makes sense in the long term. So that's why we have this gain block here. And that's why we have this bias removal term here, to actually get something that is useful in the end. And then of course we can write to the hardware, so we can actually make something happen. And this is an example of what we can do here. For example, our input to move our car model around, we need to actually limit the force, that we make sure that we don't go beyond the physical limits. Then we have a conversion gain here. Then we have to make sure that we actually don't hit the electrical limits. And then we have an amplifier gain that we have to take into account before we can actually apply the signal. And this is just something that's quite nice to know and quite nice to do, and particularly for students, something that they may not think about. Because when I recall from my education, it was always like, oh yeah, you can simulate everything very nicely, but you never think about how to actually connect it to hardware. And this is a very neat way of doing it. And similar to the simulation model that I showed you before, we have our active suspension up here, and this is in its own subsystem just because it's slightly more complicated now. We have our observer down here, which we are not going to use at the moment. And then we have a choice of controllers set up here, that we can then choose which we want to actually apply. So if we follow the path of our switches, we use our system states via an LQR gain, and then go through this block here and then go back as an actual input to the system. So if I now connect to our target, then it starts moving. And we can see, oh, this is quite oscillatory. This is just because we actually designed a controller that did not perform well. We saw it in our simulation before that this controller did not perform well, so we wouldn't really expect that this controller would do well now. However, if I change to a controller that we designed before with different weighting matrices, we actually get a quite different result. And now you can see that the car model is settling quite quicker to its actual state. So this is quite a nice way to get the students started on actually doing control design with hardware in the state space and doing LQR design. Now, to be honest, we kind of cheated a bit here, because we assumed that we have all the system states available right here in this line to actually do our LQR design. We don't really do have this benefit in the system. The only information that we really have is information about our accelerometer and our deflection from our base of the unit. That's about all we have. So really, from the way that we actually reconstruct our other system states is actually by using a lot of filters. So we're using a lot of high-pass filters to actually get our second derivative terms to actually reconstruct our signal here. And using high-pass filters works quite well, but high-pass filters have always the issue that they amplify noise quite significantly. So our output signal will not look too nicely and will not be smooth. And usually, if we can get a smoother signal, then we would expect something nicer to see. So just to give you an example of how our system states actually look, we can go into the scopes here, and I'm just going to rerun the simulation, rerun the hardware, and then we can actually have a look at these states for a second. And then if I go here, we now see 4 signals on top of each other, and they're moving in accordance with the active suspension, which you would expect. However, there's one thing that I need to point out, and that is, give me a second, if I zoom in here, we see this red signal is quite fuzzy. And this fuzziness is actually coming from sending our encoder signal through a derivative filter to actually get a derivative signal. And this is not really nice. Like, it's quite, we would rather have it to be a straight line or a straight-ish line. So this is something that's not ideal. For our system model in particular, we also need a second derivative to actually get our output. And that is something that is quite an issue. If we have to do a second derivative, then we actually end up with quite a noisy signal. So this is actually the output of our second derivative filter to actually get the acceleration of our car model. And you can see the noise has been greatly amplified, and the signal is no longer even close to being smooth, even though we run it through a second order filter. However, if we use the accelerometer that is installed instead, we get a very smooth signal for the very same motion. So this is actually preferable as an output that we can use for our design. Just to complete the discussion about this, I can actually show you the error between the two signals, and the error is quite significant at times. As we would expect, since we are using derivative filters, we have quite some noise in the background. So the mean is fairly close to zero, but we have a large variance in our system. So the obvious thing to do is actually to design a proper observer. Now, the idea of the observer is that we get something that can only use the output information that we have, that we can directly measure, and then try to estimate all our unknown system states with this information. And the way we do this is quite simple. We basically say, we know all this information about our system. We have this wonderful state space model of our system. How about we just copy this whole system and assume that our system is a perfect copy of what we have, and simulate that perfect copy, give it the same input, and then use the difference in the output of what we think happens and what actually happens, and send it through gain, and then actually make this whole system approach our actual states that happen. And this is exactly what's happening here. We're taking our input, that is the same input that goes to our actual plant, send it to our B matrix. Here's our A matrix, here's our C matrix, and our D matrix. And then we take the difference between our estimated output and our real output, send that through gain, and input that into our observer system. Now this gain here is designed that the eigenvalues are zero, so that's a stable gain, and that this basically means that the error signal will decay over time. And that is also the thing that becomes quite interesting for students to discover, that decaying over time does not necessarily mean instantly decaying, and again a choice of weighing matrix becomes important. So how do we design this? In MATLAB, well, there's several ways to do so. So for example, I could say L3, and here what I like to do is actually use the duality of our controller and observer design, which means that the problem of controlling a system is a similar problem to the problem of observing a system, and they're similar in a way that I can use the very same command that I used to design a controller for my A transpose matrix and C transpose matrix, together with two weighing matrices, transpose the result, and I get a wonderful observer gain. And we call this L3. And this is basically our L3. Now, what makes sense to do at this point is actually look at your result and see if that is a sensible result. Meaning, we know we have two outputs of our system. We have our deflection of our car model, and we have the accelerometer reading of our car model. So we have two outputs, and we are receiving a 4x2 matrix here as a gain, and that makes perfect sense. If we vector multiply our 4x2 matrix with a 2x1 vector, we get a 4x1 vector, which is exactly the size of vector we would expect for our observer. And then going back to our simulation model, I can now actually set my L to be L3. And then go back from actually tapping directly into our system states, but rather using the observed states instead as feedback for our LQR design. And this whole setup, if I have an observer design combined with an LQR design, that's what we call an LQG design. Now the weighing matrices, I should probably point out at this point that we used here, my W and my V. These are estimated covariance matrices of our noise values. So to go in a bit more detail, our W basically captures what we expect our system noise are, and our V matrix captures what we expect our measurement noise are in the system. So this is something that if you want to simulate it quite nicely, you can, for example, just add some Gaussian noise here for our system noise and some Gaussian noise here at this node for our measurement noise, and you can kind of capture it and see if it all works. But this is a simulation, so we would expect it to work quite well and quite as we expected. So let's just run this again and see what happens. And as we can see, this is quite similar to what we had before. Now, this is still oscillatory, but this is because we chose a gain that was quite oscillatory, because we had a way matrix that wasn't ideal. If I go back and use a gain that I designed before, and of course I should probably stop the simulation before I do this. Just say this and then restart it all. Then I end up with a quite nice response again. And this is noteworthy here, that this is actually only using the output information to reconstruct all our system states. And we get a quite nice result that actually, where the controller actually uses all of our system states. So this is quite nice. Now, what's interesting to look at here is actually our error between our estimated state and our actual state. And as we can see, in the scope here it's 0. So I'm just going to restart it to show you what the error looks once the observer gets started. To actually make sure that we have an error that we can actually get rid of, I actually set up our observer to have slightly different initial conditions than our actual system has. And this is, once again, one of these things that you have to do if you only do pure simulations, and that you do not have to do or worry about if you actually do it with hardware. Of course, hardware is going to throw enough sticks in your way that you actually have to deal with, and you don't have to make your life harder by simulating things that you don't actually need to worry about. So just that you are aware of, I have different initial conditions for my observer and for my actual plant. And if I start these and then initially stop it right away, and I look at my scope again, I can actually see, oh yeah, there was some errors at the beginning, and they were actually quite significant, but within a few seconds, or even less than a second, these errors are gone. And these errors are gone for good and don't come back, because now our systems are in sync. And this is a really nice simulation. However, simulations aren't what happens in real life. So if we do the same thing now in our actual model, with the hardware, I can go in here and change my observer gain to L3, I think it was. And now we have technically the same setup that we have in our simulation, except that rather than simulating our active suspension, we have the real active suspension connected. So now I connect to our target again, let it run, and you can see it move, and you see something that you would expect. So you see that our controller is working, that it is stabilizing our car model up here, but there is some slightly higher oscillation going on than we had before, where we actually used our filtered states. So why is that? Well, let's look at the error of our signal. And this is a real-time update of our error. So you can see this signal is changing quite fast, and I'm just going to post it, that we can actually have a closer look without it refreshing constantly. And this is just our observer error. So if you recall from the previous case from our simulation, once our observer error was 0, it stayed at 0 and never left from 0. Here, every single time we have a change in our reference, meaning our road surface model, we actually have a new observer error in both signals. So we actually have these fluctuations, have to deal with them, and have to sort out what to do with them. Moreover, if you actually look at our system states, the difference between our actual states and our observed states, then you'll see, even though we are well into the over 35 seconds of our run of this controller, we see there's quite some fluctuation going on, and this is stretching over all our signals. And this is to be expected, because this is actually hardware. we have a very nice and accurate model of our systems and can actually design a controller that is well suited for this, but it will never actually behave exactly as you want it to be. And this is just because hardware changes its characteristics with slight variations in temperature, humidity, and all kinds of environmental factors. And once again, you can model this with like white Gaussian noise or anything else, and measurement, and a system noise. But this is much nicer. You don't actually have to artificially input some noise and some issues in your system. You can actually just deal with what you have. Now, this is basically how we can do the observer design. Since we have the chance to actually estimate our system state with filters and do this design where we get very noisy ideas, we could also choose not to use our accelerometer data for our car acceleration, but we could also use a second order high pass filter to actually get our acceleration from the car from our encoder readings only. Just to give you an idea how much this may mess with the overall result, I'm just going to switch this over here, and you'll see a significant degradation in performance of our observer. And this is just because now our signal will be much more noisy. This is the same scale that we had before of our observer error, and you can see now this observer error is all over the place. And this is just because now we're actually having a second order high pass filter amplifying all kinds of noise that we don't really want. So this just shows the difference that we actually encounter. This is not the right one. When we're dealing with a high pass filter rather than an accelerometer. So this also is a nice way of showing if you have access to proper sensors, you actually can significantly improve your results. But if you don't have access, you can still most of the time generate your desired data, but it will be very noisy. So in this case, we have a peak that exceeds well over 6 here, and before we were well within 0.3 of an observer error. So that is quite significant. And nonetheless, it works. And this is basically it from my end so far. So I would hand over to Tim if there's any immediate questions, and would be very happy to assist you or answer some more questions within MATLAB. And actually, before I hand over to Tim, I just wanted to point out that we can do something similar with LabVIEW. This, for example, is a LabVIEW panel that we developed, and this is just a simulation of our system. And you can see here. This is our system matrices, once again as we expect them, and then we have our plotting tools here. We can change our gains on the fly, similar to the MATLAB environment, and we can actually update our closed loop pole locations for the controller on the fly. So I can just run this and say use this file for my active suspension, and then I get actually my real-time updated scopes, what happens, and then I can just change the gain and see, hey, what does this gain do? Is this any good if I do it like this? Oh, this makes the system unstable, so I don't want to do that. And so I can basically play around with a lot of gains and see automatically what happens. And this is quite a nice way to tune it. And once again, I managed to make our whole system unstable, so I'm gonna go back and see if the system may recover. And it does not, so I have to stop the whole thing. And we started with a more appropriate value, and then we see it can control it once again. And this is just a very nice way that you can actually see how changing one gain can have a significant influence on the overall performance of the system, and how you actually have to have stable poles to actually get a very nice output. And even though this is just a simulation here, you can of course use LabVIEW to interface with the hardware directly and do pretty much the same as I showed in the Simulink environment with LabVIEW.